Welcome everyone. So we're doing cloud today, and cloud is a very different subject from everything else we cover in the course. Normally we would want to understand what's going to happen with hurricanes, what's going to happen with mountain glaciers. Are we seeing more droughts? Is sea level rising and why? In this case, it's all about the uncertainty in climate projections. Clouds are the main reason that when the projections for the 21st century are reported, there's always a large range, say 2 to 4 degrees for doubling of CO2 or such. And we want to understand today how clouds are formed and what role they play in climate, and why is it that clouds lead to this large uncertainty in climate projections. That's the plan. Okay, so here is the projection of the IPCC from 1990, so one of the first reports. You have the business as usual scenario, and you have a best estimate, low estimate, and high estimate, and the range is roughly 3 to 6 degrees. Fast forwarding to the most recent report, the one that was just released recently is still in draft form, but it's not going to be very different. The range here is 3 to 5.5 degrees. So 25, 30 years later, the uncertainty did not decrease. There are many reasons for that, but clouds are a major one. Okay? So why did that happen? And the answer is this. Okay? Great. So let's start with what are clouds. So pretty straightforward. It's aggregates of water droplets and ice particles, depending on the height in the atmosphere. Higher clouds tend to be colder and therefore tend to be ice particles. These droplets we're talking about are really small. So they tend to be in the range of 1 to 100 micrometer. Here's a human hair, and the thickness is roughly 100 micrometers. So a cloud droplet would be significantly smaller than this by a factor of 5 to 100, say smaller than a human hair, the thickness of human hair. And you also have here a typical raindrop, which is a couple of millimeters. So you can tell that the difference between cloud droplets and raindrops is pretty significant, obviously. So we said that. And the distance between clouds, if you have to come up with a number, it's roughly 1 millimeter. So they're pretty densely occupying the cloud region, small droplets densely occupying the cloud region, and then they have these significant effects on radiation that we'll talk about today. So some orders of magnitude. Would anyone want to guess? So if you take all the water in the atmosphere, water vapor, and condense it to the ground, what would be the thickness of the water layer that will be at the surface if you do that roughly? Turns out to be 1 inch. Does anyone want to suggest what the similar thing, if we take all the water in clouds, what thickness would that give us? So remember, clouds are made of droplets now, not water vapor. This tells us 0.08 millimeters, so 300 less than the water vapor. So we're talking an extremely small amount of water in these clouds, and still they have a totally dominant effect on the radiation and therefore the energy balance of the Earth. So very, very small amount of water still playing a dominant role. That's part of the difficulty. Okay. These are 4 different models. And what's shown here is something known as the liquid water path. That is, at each meter square of the atmosphere, you see how much water vapor is there above us, or how much water in clouds is there above us. And that number is referred to as the liquid water path in the case of water in clouds, liquid water in clouds, as opposed to water vapor or ice in clouds. And you can see that the average number is roughly 80 to 100 in all of them. But look at the variability between different models. I mean, look at these blues here versus the reds and greens here. These are very, very different projections for where the clouds are and how much water there is in these clouds. And this model disagreement is a reflection of the uncertainty that we have with the simulation of clouds, and therefore in the simulation of the role of clouds in a future climate change. And we'll see today why there is such a range of disagreement between the models. Okay, so let's talk about clouds and radiation, because the main role of clouds is when they interact with radiation in the atmosphere. So first of all, a reminder, shortwave and longwave radiation. So shortwave is the radiation coming from the sun, if you remember. This is this peak. And wavelength is 0.4 to 0.7 is the visible shortwave, while longwave radiation is the radiation emitted by the Earth itself. And the wavelength here is 5 to 30, so we're talking a significant difference between the wavelength of the shortwave radiation and the longwave radiation, and therefore they're going to interact differently with clouds. Okay, so shortwave and longwave. So this is sort of a big picture situation. So let's see, what can clouds do with radiation? So if you have incoming shortwave radiation here, it can be reflected by clouds. So this is the cloud albedo, the reflecting shortwave radiation from the sun. This is an important role of clouds. We'll see later that clouds double the reflectivity of the Earth. So half of the reflectivity of the Earth is due to these clouds, even though they have so little water in them. The other effect is a greenhouse effect. You see here, these clouds absorb long-wave radiation that come from the surface. So it's the clouds and the atmosphere, not just the clouds. And then they emit the radiation back down and up. And this is part of the greenhouse effect that we discussed. But an important part of this greenhouse effect that we discussed and models using this two-layer model before is due to clouds, and we'll talk about that more today. All right, nice. So let's see. So now we want to talk about the separate effects of clouds on long-wave radiation versus short-wave radiation. So here the size of the droplets makes a big difference. So as we said, the droplet size is 1 to 100 micrometers. So we have to separate these to long-wave radiation and short-wave radiation. In the long-wave, because clouds are made of water, they absorb almost as well as black bodies. So the emissivity of clouds tends to be close to 1, and they absorb basically almost all of the long-wave radiation that's directed at them from the surface, say. And then they re-emit it efficiently. So now clouds and shortwave, when cloud droplets interact with shortwave with visible radiation, this is referred to as mis-scattering. They scatter the radiation. So if a ray of radiation, of shortwave radiation, hits an area in the cloud with many droplets, it would be scattered in all directions, also forward. So there would be a forward scattering, backward scattering, and scattering to the sides. The scattering is such that there's no wavelength dependence. All wavelengths of light are scattered with the same efficiency, as long as the droplet size is larger than the wavelength of the radiation. Okay? And that's referred to as mis-scattering, named after Gustav Mie. Here's this person right here. Now, for a given amount of water, if we have many small droplets as opposed to a few large droplets, then the area that the radiation sees when it approaches the cloud is a larger area of water. So if for a given amount of water, if the cloud is made of small droplets as opposed to large droplets, it would be more efficient in interacting with radiation. And we'll talk later about what determines whether the droplets will be large or small in the cloud. It basically has to do with aerosols, small particles in the atmosphere around which condensation occurs. Yes?
Could you explain one more time why smaller droplets would be more efficient at scattering? Because I think intuitively that the larger the droplet, the more running into each other would happen.
Yeah. So suppose we have a certain amount of water, and I distribute it once here to 3 droplets and once here to many small droplets. A radiation here could just go between the droplets, while here it's not likely to go between the droplets. I think it's as simple as that. The surface area of the small droplets is larger than the total surface area of the large droplets, and also is the cross-section area that the radiation sees when it approaches. This quantity is what it's all about, cloud radiative forcing. So we define cloud radiative forcing. We define it to be in the following way. So suppose we think about long-wave cloud radiative forcing. So we simulate climate, and we quantify the long-wave radiation that's coming from clouds to the surface. So that would be the long wave radiation with clouds. Then in this climate model, we remove the clouds and we calculate again how much long wave radiation is reaching the surface. That would be this one. The difference is the net effect of the clouds on the long wave radiation, typically estimated either at the surface or at the top of the atmosphere. And that's referred to as either cloud radiative effect or cloud radiative forcing. So the units are meters square, are watts per meter square. And there's a model involved here, but the model involved here in calculating things without clouds is a radiation model. There we understand the physics. There's not much uncertainty there. So this is a quantity that we can estimate fairly well. Same thing with shortwave, of course. If we have clouds, they could block some of the sunlight, so we could measure the shortwave radiation, the sunlight at the surface with clouds, and then we remove the clouds in the model and calculate the shortwave at the surface again, this one, and the difference in this is the shortwave cloud radiative forcing. And both of these are critical, as we'll see in a second, in terms of numbers. So the sum of the two is referred to as the net cloud radiative forcing. Okay, so now two slides about the shortwave cloud radiative forcing and the longwave cloud radiative forcing. So starting with the shortwave, as we said, the clouds don't absorb very much shortwave radiation. Why is that? If you think about it, visible light goes through water. Water is transparent to visible light, right? You look through a glass of water and you can see the other side, so the visible light is able to go through the water. So there's no reason to expect water to absorb shortwave radiation based on our everyday experience. But the small droplets can still reflect the shortwave radiation. Low stratocumulus clouds are the ones seen on the left here. These clouds are in the first couple of kilometers above the surface. They are very white. These are the clouds you see often when you fly in an airplane and you look down. And they have a very large albedo. So low stratocumulus clouds have a significant shortwave cloud radiative forcing as a result of their reflectivity. On the other hand, cirrus clouds are these clouds. These are these wispy clouds that are much higher at the altitude of 4 kilometers and above, basically. And you can see the sunlight through them, which means that they let shortwave radiation go through, but they are exceptionally effective at trapping longwave radiation coming from the ground, as we'll see in a second. So cirrus clouds don't have a significant shortwave effect. This is what I mentioned before, that clouds effectively double the reflectivity of the Earth. It would have been 15% of the radiation from the sun being reflected. Due to the clouds, it's 30% roughly is being reflected. So that's a huge effect on the radiation of the Earth, given how little water there is in these clouds, if you remember. So let's see. Suppose we're getting some radiation flux here arriving from the sun. This reflected part would be the albedo times F, and the transmitted part would be F times 1 minus alpha. That's albedo. Albedo is the reflectivity. Emissivity is something completely different. When you have a cloud of temperature T, the emission of long wave radiation now would be the emissivity times sigma T to the fourth. This is the emissivity. So it's how effective is the long wave radiation by the object, in this case the atmosphere, the cloud, measured by this emissivity constant epsilon that is constant between 0 and 1. 1 means that this is essentially a black body which is perfectly effective in absorbing and emitting long wave radiation. Doubling of CO2 amounts to 4 watts per meter square. A 10% in change in clouds would have exactly the same effect. So if in a warm climate the clouds change by 10%, that would be equivalent to the effect of CO2. Now that effect could be either enhancing the CO2 or opposing the effect of CO2. That we'll have to figure out. Okay, so this is shortwave cloud radiative forcing. Let's move to longwave cloud radiative forcing. So clouds don't reflect long wave. They simply absorb it, essentially. because they're made of water, and water is very effective at absorbing long wave radiation, as we know. And we talked about what emissivity is just a second. And the emissivity of clouds is very close to 1, so they are very effective at absorbing long wave radiation that is sent to them from the surface and at sending back that radiation both up and down. We have the long wave cloud radiative forcing, and the net effect of the clouds or long wave radiation is that they trap 30 watts per meter square. So if not for the clouds, the long wave, the downward long wave radiation would be smaller by 30 watts per meter square. So let's see, what is the net effect of clouds? It's going to be the clouds block the sunlight, but then they trap some of the heat. So the net effect is, say, 10 to 20, 10 to 15 watts per meter square cooling effect by these clouds. So clouds in the present day climate cool the surface because the shortwave reflection overcomes the long wave emissivity effect. The question, of course, is what happens to the long wave cloud radiative forcing, to the shortwave cloud radiative forcing, and to the net cloud radiative forcing in a warmer climate. This is where the uncertainty will come in and everything. So let's summarize what we know about high clouds and low clouds and explain a bit more these issues. So the shortwave cloud radiative forcing, or if you want the albedo, the cloud radiative forcing of the cloud radiative forcing in the shortwave is simply due to the reflectivity of the cloud, so that's an albedo effect. Is controlled by the cloud droplet size and by how much water there is in the cloud. These are these two examples of large droplets versus small droplets that we drew before. And we talked about the fact that low clouds have a high albedo. On the other hand, think about the following. So let's say these low clouds have a small long wave effect. Let's see why that is the case. So here's the surface, and we have a cloud here at a height of, say, 1 to 2 kilometers. So we have long wave radiation is emitted from the surface and hits the cloud, and then that is re-emitted both up and down by the clouds. Now, because the clouds are close to the surface, the temperature is not very different from that of the surface. So if the temperature here is Ts, and this is the T cloud, then T cloud is not very different from T surface. So this emission here, sigma T cloud to the fourth, is roughly equal to sigma T surface to the fourth. So the fact that all of the radiation was absorbed by these low clouds and then re-emitted didn't really make a big difference on the emitted radiation from the top of the clouds, and therefore the clouds didn't really block the long wave radiation from the surface. So even though all of the radiation from the surface might have been absorbed by these clouds, it's re-emitted upward almost at the same temperature, and therefore there's no large effect on, no large greenhouse effect of such low clouds. Okay? But if the clouds is high, where the temperature is very cold, then T cloud is very small. So this is for low clouds. But for high clouds, we have T cloud is much smaller than T surface, and therefore sigma T cloud to the fourth is much smaller than this, and the radiation is in fact trapped by the clouds and is not allowed to continue upward, and therefore high clouds have a very strong greenhouse effect, and low clouds don't have a strong greenhouse effect. So the bottom line is that low clouds have a strong reflectivity, strong cooling effect. High clouds have a strong greenhouse effect, warming effect. So I'm hoping this would be mentioned here somewhere. So look at the bottom here. Low clouds have a small long wave effect and large albedo. So they have a net cooling effect, while high clouds emit at cold temperature at the high altitude in which they are, and therefore they have a strong net long wave warming effect, while their albedo is very small, so they have a net warming effect. Okay? High clouds warm, low clouds cool. Let's see. So here's the surface again. Here's the temperature as function of altitude. So this is T of Z. Temperature as function of altitude going down at a few degrees per kilometer. We're assuming that wherever the cloud is, it takes the temperature of the surrounding air. So if the cloud is high, this entire cloud is going to be cold. If the cloud is low, this entire cloud is going to be relatively warm. So now when the radiation is absorbed by this one, it will be re-emitted at a similar temperature of the ground. But if the radiation is absorbed by this one, it will be re-emitted at a very cold temperature. Okay. So let's look at the results for 1 second, even if you're not done. So you see two models here. These are two different climate models. GFDL stands for the Geophysical Fluid Dynamics Laboratory. This is the NOAA lab in Princeton, New Jersey, one of the major centers for climate research in the world. And this is a UK one, the Hadley Center, equally prominent. So these are very serious efforts for climate model development. These are the clouds they predict for the present day climate. These are the clouds they predict for probably the end of the 21st century RCP 8.5 scenario. And this is the difference. Look at the difference here versus the difference here. There's plenty of red in the Arctic, so more clouds showing up in the Arctic in this model, but nothing in this model. You look in anywhere else almost. Look at this red patch here and blue patch here. They hardly exist here. So these models give very different predictions of how clouds might change in the future. And this leads to a very large effect on the temperature. So let's look at that. So this is the change in temperature in the two models. So in the Arctic, the surface air temperature, SAT, doesn't change much, and here it does change by a lot. This is exactly the place where the clouds were very different, right? And these are the shortwave and longwave cloud radiative forcing effects. You can see some differences here. So basically, the point is that each of these two very prominent models predicts a different cloud distribution change in a warmer climate. And as a result of that, the surface temperature that they predict is, the change to the surface temperature is also very different. So look at these figures, and especially the numbers that popped here. You see this? So the global mean shortwave effect is cooling by about 50 watts per meter square. The global effect, the long wave effect of the clouds, is warming by 25-30 watts per meter square. And there's a net cooling of 20 watts per meter square. And again, the question that we're asking is how much would these numbers change in a future climate? The difficulty is that these are two large numbers and a significantly smaller difference. So if the large numbers each change by a small fraction, the difference would change significantly. Okay, this is the difficulty. Okay, so now we want to talk about cloud formation. What is the process by which clouds form, and why is it so difficult to simulate and understand it? The process goes like that. So suppose we have rising air. So think about the rising air parcel starting from the surface going up. Here's the surface. Suppose this is an ocean. The ocean absorbs shortwave radiation from the sun and warms up, and then there's a parcel of air that is then heated by exchanges of heat with the ocean. It becomes warmer and therefore lighter, and it starts rising up. What happens to the air as it rises up? It encounters a lower pressure because the pressure goes down with altitude, obviously. So if the pressure goes down, what happens to the temperature? It goes down as well, right? So the temperature goes down because the pressure went down. This is referred to as adiabatic cooling. if the temperature, if the parcel was going down and being compressed, it would be warmed up. This warming and cooling does not involve exchanges of heat with the surrounding air. It's simply the change of pressure that leads to this change in temperature. Does that hopefully rings a bell for many of you? High school, I assume. Okay. At some point, the amount of water vapor that can exist at a given temperature in the air is a function of the temperature. So if I cool the temperature, can there be more or less moisture then? Less. That's right. Colder air has less moisture than warmer air. So at some point when the temperature decreases enough, the moisture that existed in this air parcel, because it was in touch with the ocean, so it's pretty moist, would have to start condensing. So now you're forming droplets. When you're forming droplets, you're releasing, the process of condensing water vapor into droplets releases latent heat. We talked about this in a different context, in the context of hurricanes, if you remember. So now this air parcel is heated by this release of latent heat, and it becomes buoyant again, and it's rising again. And as it's rising again, it's encountering an even lower pressure, cooling again, condensing again, and so on and so forth. As soon as we have condensation, we effectively have a cloud, right? So this is where the cloud formation begins. And this process is referred to as moist convection. So this generally is the process by which clouds form. We're going to quantify this in a second. So the temperature decreases, and the air parcel humidity matches the decreasing saturation humidity. Saturation humidity is the maximum amount of moisture that can exist at a given temperature. These are all things that we just described. Now, this updraft can happen in different circumstances. We just described one here, where the air parcel is heated by the ocean and therefore rises. But suppose you have a situation where there's a mountain and there's airflow here, so the air will go up. As it goes up, it encounters lower pressure, and then again, it will cool as a result of that, condense, and you'll get cloud formation. So here's another one explaining what adiabatic heating and cooling is. This is a really nice demo, so let's look at that.
Wow.
Nice, isn't it? So compressing air leads to warming, and doing the opposite leads to cooling. So if we allow the pressure to go down, the air expands, it will cool. That is the reason for the cooling. So if you think about it, in the atmosphere, the temperature goes down with the elevation, and that is because the pressure goes down with elevation. So this is essentially an explanation for why temperature goes down as we go up in the troposphere, and we'll quantify this in terms of equations in 1 second. Okay, here's another one that's really nice, I think.
At all. You don't want to get any matches, anything near this at all. So our valve stem goes up here. We're going to do the same as before. We're going to increase the pressure. 1, bam, and there's our cloud.
Amazing, I think. Questions about, so what we saw now is as the bottle was opened, air escaped, the pressure went down. This led to cooling of the air that remained in the bottle, and the cooling led to condensation, cloud formation in a bottle.
Cools that fast?
You could see it. Nice. Okay, so let's go through now the simple math behind the formation of these clouds. Lapse rate and moist convection. Let's start from the concept of saturation as specific humidity. So there's first of all the concept of partial pressure. Moisture, the water vapor is a gas, so part of the pressure in air is due to the moisture and part of it is due to the dry air. And saturation specific humidity is essentially a measure for that. In this particular case, it's defined to be the, say, the weight in kilogram of water vapor divided by the weight by a kilogram of moist air. And this is the maximum of that at a given temperature and pressure. So T is temperature, P is pressure. So given the temperature and pressure, there is a maximum weight of water vapor in per kilogram of moist air, and that is the definition of saturation specific humidity. And we can denote that as Q star of TNS, of TNP. Okay? In order for us to understand why the atmospheric temperature goes down with height and so on, we're going to use an energetics argument. So consider the following quantity is the energy of an air parcel. So this is referred to as the moist static energy of an air parcel is given by three components. So there's the Cp times T of Z plus L times Q of Z plus Gz. I'll give you a second to copy this, and then I'd like to explain each. All right, so let's see. This is the specific heat of air, and this is the temperature at the elevation in which we are. This together is the internal energy. It's simply the energy due to the temperature of the parcel. This thing here is the potential energy. And it is the energy that the parcel has due to its elevation in a gravity field. You know, it's like mg, potential energy mg, written in this way. And this last part is the energy that could be released into the air parcel if the moisture is condensed. Okay, so this is the contribution, potential contribution to the energy of the parcel due to potential condensation that might occur. Q is the specific humidity. So that's Q. So it's not the saturation specific humidity, it's just the specific humidity, which is the weight of water vapor in kilogram per kilogram of moist air. And we multiply this by L, which is the latent heat of evaporation / condensation. And together this would give us the heat that would release into the parcel if all of this moisture condenses. So that's this sum of three terms must be conserved as long as this air parcel does not mix with the surrounding air. And when it does not mix, we call it a diabatic motion, a diabatic process. So what we want to see now is how the conservation of this moist static energy can allow us to calculate the temperature of an air parcel as it rises up in the atmosphere. So consider an air parcel rising from the surface where Z is equal to 0. Its moist static energy at the surface, which I'm denoting MSE subscript S, is going to be equal to Cp times Ts, this is the surface temperature, plus L times Qs, which is the surface specific humidity. And as the air parcel rises to some other height, it's going to conserve its moist static energy as written right here. So the temperature will change, the pressure will change, the height will change, but the moist static energy will remain the same. So first, suppose the parcel rises just a bit so that there is no condensation. That is Q of Z is equal to Qs. We're rising to a height Z. There's no condensation, so the amount of water vapor remains the same in the parcel. In that case, we can write the moist static energy at a level Z is equal to CPT plus LQ of Z plus GZ is equal to the moist static energy at the surface, which is equal to CPTS plus LQS. This is the statement saying that the moist static energy at the surface is the same as the moist static energy of the same parcel as it rose to a height Z. Okay. So now we said that there's no condensation, so the moisture, the specific humidity remains the same. So Qs is equal to Qz, and we can therefore remove this from both sides of the equation. And there's no Gz here because Z is 0. So we get the following statement. Cp T of Z plus Gz is equal to Cp Ts. And we refer to this one on the left as the dry static energy. And this is the dry static energy at the surface. So dry static energy is the same as moist static energy without the contribution of water vapor, because at this point the specific humidity does not change, so we don't need to worry about it. It drops out of the equation, and we're left with an energy conservation statement that involves only internal energy and potential energy. So that tells me that T of Z is equal to T at the surface minus G divided by Cp times Z. This number right here is basically 9.8 degrees Celsius per kilometer. It's the dry adiabatic lapse rate. Let's write it down right here. As we raise the parcel even more, it will start condensing, and then we'll have to use the MSE again. But we already learned something important. We learned why is it that air gets colder as we go up? Because think about what happened here. We started at a certain temperature Ts. We went up. The total energy is conserved. But as we go up, some of the energy of the parcel must be converted to potential energy. So the internal energy must be decreasing. And if the internal energy is decreasing, it's basically telling us that the temperature is decreasing. So it's a simple statement of energy conservation, so far not involving any moisture or phase changes of water. And this rate of change is what we get as long as the air parcel does not condense. The cooling as it goes up would be roughly 10 degrees Celsius per kilometer. That's a lot, right? You go up, you hike a mountain of 1 kilometer, you've lost 10 degrees Celsius. Okay. So now in the next phase, the parcel keeps rising. And now it's cold enough at some point that we're beginning to condense water vapor. And we're losing Q. So some of this Q would be lost because the water vapor turns into water droplets. So let's see how this calculation is modified as a result of that. So next, suppose the cooling led to condensation. We want to calculate the temperature in that situation as well. So once condensation occurs, we can assume that Q of Z is equal to the saturation specific humidity. So it's going to be equal to Q star of T of Z and P of Z. So this Q star is the maximum amount of specific humidity that can exist at this temperature and pressure to which we arrived. And our assumption is that condensation occurs such that the moisture content measured by specific humidity goes down to this saturation at that level. Okay? So as a result of that, we can write the following equation: Cp T of Z plus L times Q star of T of Z and P of Z plus Gz is equal to the starting point, which is the moist static energy at the surface. So this is the energy conservation if condensation occurred. And before we had Cpt of Z plus G plus L Q S plus G of Z equal to moist static energy at the surface if condensation did not occur and Q of Z is still equal to QS. These are the two situations that we've looked at so far. Okay? So now if you think about this, this is a known function. If you remember, you plotted it in the hurricane section. So this is an exponential function of the temperature. It's a complicated function of the temperature. So Cp is a known constant. T of Z is what we don't know. This is the temperature at an elevation Z that we're trying to calculate. This is some function of that temperature. Z is known because we know at what height we are. So you can think about this as being an equation for the temperature, and we'll see how to solve it in a second. And once we solve it, we know what the temperature is at elevation Z thanks to this energy conservation. Okay, so let's just combine these two together into a single form, and then I'll show you how it's actually being solved. So we can simply write both of them as combined form. Moist static energy at the surface is equal to Cp T of Z plus L times the minimum of Qs and Q star of T of Z, P of Z, plus Gz. So this is the equation for T of Z that we need to solve in order to find what it is. And it's a straightforward equation to solve. I'll show you now how to do it. So think about this as a left-hand side, right-hand side. So I could do the following thing. I could write either left-hand side or right-hand side as function of T of Z at a given specific Z. So the left-hand side is simply a constant. It's this moist static energy. It has some value. We know it because we know what the moisture is at the surface and we know what the temperature is at the surface. Right? This is equal to CPTS plus LQS plus G times 0. So I know this. I can plot this as a straight line. The right-hand side is a more complicated function because it depends on this Q star, which is an exponential function, so it's going to look like this. And at some point, they're going to cross each other, and this is the temperature that we're looking for that solves this equation. So this is how we can graphically calculate the temperature from this equation. We plot the right-hand side, we plot the left-hand side. You're going to do this in 1 second, and that's how we're going to decide what the correct temperature at the level Z is, assuming that there was no mixing and adiabatic rising and all of that. And it's all based on the energy conservation, including internal energy, potential energy, and the energy due to the conversion of water vapor into heat due to condensation. All right. Physically, what happens, if you think about it, is the following. This is the surface. We're starting to rise, and the temperature goes down according to minus G divided by Cp, right? Remember this, minus G divided by Cp times Z. That's the temperature initially. At this point, condensation starts. So here's my question to you. As we go up now, would the cooling be faster or slower as we go beyond the level at which condensation begins?
Slower.
Why?
Because as you start condensing, latent heat is going to be released.
Exactly, yeah. So, so now we call this level the lift condensation level, LCL. Beyond that level, the slope is going to be a bit less sharp because as we go up, the cooling due to the adiabatic cooling due to the decline in pressure is compensated partially by the fact that we're releasing heat due to the condensation of water vapor. So this is the moist, this was the dry adiabatic lapse rate. And now this is the moist adiabatic lapse rate, okay? Yes, I'd like to do one more thing that involves derivations, and then we'll be able to send you to do these calculations yourself. And the issue is this thing right here. This function, the saturation specific humidity, is a function of temperature, but it's also a function of the pressure at the level Z, and we don't know that pressure. So we want to calculate it, and there's a very simple derivation of what it is. So let's try to calculate that. So this would take us a couple of minutes. So this would be calculating P of Z, or if you want, the hydrostatic approximation. All right. So far we dealt with energy balance. Now we're going to move to force balance, momentum balance. So consider an air parcel. This is up. Consider an air parcel of height dz from here to here. This air parcel feels some pressure from below. This would be P of z, is the pressure it feels from below that pushes it up. And then it feels a pressure, P of z plus delta z, from above that pushes it down. Which one is going to be larger? Emma? From below, because we know that in the atmosphere pressure decreases as we go up, so we expect the parcel to feel a stronger pressure from below. What happens to this pressure as it feels a stronger force from below? You would think that it rises, but you look at the air and it doesn't necessarily rise everywhere, so something must be balancing this pressure force. What would that be? Yeah, the weight of the particle is exactly balancing that. So what is the weight of the particle? We have a certain mass that pulls it down, and this would be essentially delta z times the density times the gravity would be the mass times gravity, that's mg, per unit area in the horizontal direction. So this is the mass per unit area, and that force that pulls it down exactly balances the pressure force that pushes it up. That balance is called the hydrostatic approximation, the hydrostatic balance. So we can easily convert this into an equation for the pressure. So the net pressure force is going to be P of z minus P of z plus delta z. That's equal to, so this is essentially minus the derivative, right? The derivative is P of z plus delta z minus P of z divided by delta z. So I have the opposite here, so it's going to be minus dp dz times delta z. So if I divide by delta z and multiply by the minus, I get exactly the definition of the derivative. Hope that makes sense. And then the gravity force, we said is going to be equal to delta z times rho times g. So the two being equal is going to give us that the P dz is equal to minus rho times z. This is a P here. P is the pressure and rho is the density of air. We saw that before in other contexts. Okay, this is almost it. We need to take one more step, small step, to convert this into an equation for the pressure. Okay, stop me if there are any questions, obviously. Yes?
Will you explain the equation for gravity force again?
Right, so the force of gravity is mg, right? M, the mass of a parcel, is the volume times the density times g. The volume is essentially delta z times the horizontal area, which we take to be unit 1. So delta z times 1 is the volume, times the density is the mass, times g gives us the gravity force. Thanks for asking. Yes?
So I was wondering where the g went when you were equaling out the two sides of the equation. I think, so the gravity force was z times rho times...
Oh, yeah, this is missing a g here. No, this is wrong, sorry. So here's the correction. This is minus rho g. Thanks for that. Right, this comes directly from setting this equal to that. And we get this. That's my second red for the day. We talked about 5, I think, as being the limit. I think we're still safe. Okay, great. So now let's see. We're almost there, as I said. So the next step is the ideal gas law. I'm afraid. So we have to use the idea that the density of air is equal to the pressure divided by RT. Rings a bell, hopefully? Excellent. And therefore, we could substitute into this equation, and we get that dP dz is equal to minus G P divided by RT. Very good. Now let's see. The temperature in the atmosphere, T, would be, say, going from 300 at the surface, so smaller than that. So the temperature would go from 300 to, say, 220 or something Kelvin. Okay? 300 at the surface, 220 at the tropopause maybe. This is the range. I'm going to replace this temperature with an average temperature that is equal to 260. Let me call 260, so minus 13 degrees or so Celsius. This would be my T average. So now it's not a function of Z anymore, and I'm simplifying this equation using that. So I have dP dz is equal minus Gp 1 over RT hat. So now everything is constant except for P, and this is an equation for P, and we can solve it. Let's see how that's done. So essentially this becomes the following equation. dP dz is equal to minus P times G divided by RT hat. What's the solution for an equation? And this is a constant. What is the solution for an equation like that? What function solves that sort of thing? Someone on this side maybe?
An exponential.
Here we go, a graduate of EPS 131, you see? You should all try that. Okay, so it's going to be an exponential solution. Many of you, I think, know this, but if not, you can try. So the solution is that P of Z is equal to the P at the surface times E to the minus GZ divided by RT hat. So this shows us that the pressure goes down exponentially as we go up in height. So now we know what P of Z is, and now we can go and solve that equation for the moisture, which was our goal. Okay, that's plenty of derivations. I think this would definitely be a good point to stop. Any questions about this first? Okay, let's take a break. Okay, so now here's what I mentioned before. This is the one side of the equation, the other side of the equation, and in the workshop you'll be trying to plot both and find the crossing point, and the crossing point as function of the temperature refers to the temperature at which energy is conserved, and that tells us what the energy is of the parcel when it rose to a level Z. Are there any questions about this? We don't have to do it graphically. We could just use something called root finder. We have a nonlinear equation as function of t. We use the root finder to find what t solves it. You can see in the Jupyter notebook how that works. Let's describe the process now. So consider this parcel right here shown by the orange curve. And let's see what are the steps that occur during this moist convection. So we start at the surface, and something raises that parcel. Okay, we don't know what that is. Something leads it to rise. As it rises, you can see that the temperature is being cooled basically all the way to this point along the dry adiabatic lapse rate, as we said. At some point here, roughly here, the slope changes. So this means that this is the lift condensation level. This is where the moisture of the parcel has reached saturation, and now it starts condensing so that the moisture would not be higher than the saturation moisture. And now we've risen some more. At this point right here, the orange line crosses the dash line. The dash line is the temperature of the environment around this parcel. And when the temperature of the parcel is higher than the environment, it now becomes buoyant. When it becomes buoyant, it can rise on its own. We don't need to force it to rise anymore. So this is called the level of free convection right here at about 2 kilometers for the orange curve. Okay? And now the parcel keeps rising, condensing, rising again, condensing on its own. We don't need to push it up. We don't need to raise it. It's rising on its own because of this buoyancy that is provided by the latent heat that is released due to condensation. And that will go all the way to a few kilometers, here 10 kilometers, at which point the parcel temperature, the orange line, is what we calculate based on these equations that we derived. You'll be doing that. You'll be plotting a plot like this. When it rises again, this parcel, it becomes less buoyant than the environment, so it stops rising and it starts going to the sides. And then what you have is air with some remnants of water droplets and so on that came up. Maybe at this point there are ice particles, and they go to the sides and they create these high clouds at a height of 10 kilometers in this picture. So you have a cloud all the way from 1 kilometer to 10 kilometers, and at 10 kilometers there's horizontal flow that creates a broader area covered with these high clouds that, as we know, have a very strong greenhouse effect. And this final level here, where the density is equal to that of the environment, the temperature is equal to that of the environment, and the parcel can't rise anymore, that is referred to as the level of neutral buoyancy. So we have lift condensation level, level of free convection, a level of neutral buoyancy. These are the 3 steps that the parcel encounters as it goes up during this moist convection process. So someone asked about relative humidity. Relative humidity is the moisture, say the specific humidity, divided by the saturation humidity. And you can see that as the parcel rises, it started out with 70% of the saturation humidity at that point. It's cooling, so the percentage increases. At this height of about less than a kilometer, it reaches 100% relative humidity. Now, if you try to cool it even more, the parcel moisture at the surface, QS, is larger than the saturation humidity, and it starts condensing. And from now on, it's at 100% all the way up. Okay? So now Q is equal to Q star, all the way from here, all the way to the top. Okay, well, let's talk about the green one. The green one starts at 50% moisture. So as a result of that, you see it goes, at this point where the orange one saturated, the green one didn't have enough initial moisture, so it doesn't saturate with it. It will only saturate at this point right here. So its lift condensation level is higher than that one. That's the first thing we see here. Make sense? Okay. Next, as it rises, interestingly enough, it never crosses the dash line. So it never gets to the level of free convection where it could rise on its own. So essentially this parcel, if it were to go up and encounter this profile, it would have to be forced by something. Nothing can actually force this. So in fact, the green parcel will never rise all the way to the top because it's stable. The orange one essentially was made unstable at the lift condensation, at the level of free convection, and could rise on its own. The green one never becomes unstable and will never be able to rise to the top. So air parcels that make it to the top are air parcels that have higher moisture at the surface, because the mechanism of the rising is the latent heat release due to the conversion of water vapor into droplets. And when there isn't enough convection to feed this process, the parcel won't become buoyant and won't be able to rise on its own. And the other one that we see here is the one that has 90%, that very quickly got into the level of free convection right here, close to the surface, and then convected all the way to 12 kilometers and then exited to the sides. More questions? Okay. Now we talked about entrainment and uncertainty, right? So you understand the process now. Here's why it's so difficult to simulate this in a climate model. So what we're about to see here is cloud motions, and you'll see the the rising of air parcels, and you'll see that as the parcels rise, there's lots of turbulence going on, and they incorporate lots of air from the sides. And that entrainment of air from the sides is difficult to predict in a model because the scale of this thing is much, much smaller than the scale of a grid box in a climate model. So let's see how complicated this is. And beautiful. So you see the rising, the pressure goes down, it immediately condenses just like in the bottle. It creates these clouds. You can see how complicated the motion here is. It's not just a single parcel rising, it's a whole complicated turbulent flow. So moist static energy cannot be conserved because there's so much mixing going on. And as a result of that, we don't know exactly how to simulate this because it happens on such a small scale. And if you have a global model of the atmosphere, it's difficult to simulate these small-scale motions that are only tens of meters large, maybe, while the grid box is 100 kilometer or 50 kilometer. So what you're seeing here is the reason it's difficult to simulate these things, and that is the reason we don't predict that every climate model predicts a different cloud distribution and different changes to cloud distribution and so on and so forth. This is one reason for the uncertainty and model differences.
So when the cloud is rising between the two times it intercepts the dashed line,
Yeah.
is it still, it's continually condensing as it's going on?
Yes, that's what you're seeing here. What you're seeing here is the level of free convection is here somewhere, and the level of neutral buoyancy is here somewhere, and you could see the air rising between these two levels. Microphysics is a whole different issue with clouds that also leads to uncertainty. I have just one slide that describes this, so let's go through this. We talked about condensation. Condensation happens more easily if the water vapor has something to start with. So that's referred to as the cloud condensation nuclei. These are examples of cloud condensation nuclei. They could be volcano ashes, this could be plant pollen, it could be, I think this one is salt, and this is soot. So sea salt, pollen from plants, volcanic ashes, all of them are very small particles that manage to make it into the atmosphere. They're very light, so they don't fall very rapidly, and it's easier for water vapor to condense around these things and form droplets. If there are many of these, then we'll have many small droplets, for example. If there are fewer of these, we'll have less droplets that are bigger. So the concentration of pollen or any of these aerosols, so aerosols are small particles, right? So the concentration of these aerosols and cloud condensation nuclei determines whether our cloud would develop into many small droplets or a few larger droplets. And we need to know what is the aerosol situation in the cloud formation area. That's a whole complicated issue by itself. And that adds a lot to the uncertainty in cloud formation and what type of droplets develop in the cloud. Okay, so the aerosols could be natural. They could be dust or sea salt particles or something else, or they could be human-caused. They could be due to the contamination from some factory, or they could be a fire used by human activity or internal energy, combustion engine emissions, and so on. So they act as CCNs, cloud condensation nuclei, or high enough in the atmosphere, they act as ice nuclei to start the nucleation of ice particles around them. And they grow by deposition of water vapor. And then after that, when the droplets grow enough, they start colliding with one another. And then they grow by collision, as opposed to growing by accumulating water vapor. So these are the two phases of water droplets growth. First, deposition of water vapor, and then later collision of droplets to larger droplets. And now if we wanted to simulate this process in a climate model, which is what we're trying to do, we need to know how many aerosols are there, how effective are they at creating droplets. when would droplets begin to collide and coalesce into bigger droplets, and so on and so forth. And all of this, whether the droplets are big or small, many or few, really affects the cloud emissivity and long-wave radiation, and as well as the shortwave albedo. So we really need to know these things, but the calculation and the understanding of this is very complicated. And that's the final point here. The issue of direct effects versus indirect effects, that's a big deal. So direct effects is simply the fact that the aerosols themselves, all of these things here, absorb and reflect sunlight themselves. That is called the direct effect of aerosols. But at the same time, they also affect the distribution of cloud droplets and the distribution of clouds, and the clouds also have an effect of radiation. So that's called an indirect radiative effect of the aerosols. And both are complicated, especially the second one is complicated. So representing that in an accurate way is practically impossible. We do our best, but we obviously don't do very well because each model does something else, and the results depend on this very much. Any questions about and all of that is referred to as microphysics. These are things that happen on the scale of a droplets in a cloud. Remember, climate is a global issue. It depends on things that happen on a scale of a few tens of a micrometer, the scale of a droplet. So hence the complication. So let's look now at the lifetime of a cloud. You could see now formation of clouds and dissipation of clouds. If you look carefully in this area, you see convective motions. This rising leads to the formation of cloud, and you can follow this now. It reaches some level where it stops convecting, and the cloud is just advected by the wind, and then it dissipates because it evaporates. So this is the typical lifetime of a cloud. It's formed by convection, and at some point it starts. Look at this here. This thing is just evaporating completely. Okay, so it's formed by convection, it's advected and carried by the winds and being evaporated, and clearly a terrifically beautiful and impossibly complicated process. Questions? So I'm hoping you understand clouds have a huge radiative effect. They involve a very, very small amount of water. We talked about this at the beginning. What was it? A fraction of a centimeter of water in clouds in the entire atmosphere. And then they're very complicated when they develop, and they have this large radiative effect. So you understand why this is a complicated problem. Okay, so now there are high clouds, low clouds, there are clouds made of water, and there are clouds made of ice. Let's just look at some beautiful pictures. What do you think? Are we all as tired as I am? Okay, here. So these are low clouds. When you sit in an airplane, these are the ones you see. These are the stratocumulus clouds. Sometimes they have these shapes of cells. The cells could be open, like this, or they could be closed. Closed means that the entire cell area, often idealized as a hexagon. So these are many hexagons. In practice, they're not exactly hexagons that are covered by clouds. Sometimes the hexagons have clouds only on the edges of the hexagon. These are really beautiful things to see. So these are low clouds, and we talked about them having a large albedo, but not a very strong long-wave radiative effect. And then we have these deep clouds. So these are the clouds where you can see the rising of air and the cloud formation going up, and then you can see the horizontal spreading. What do we call the level where the spreading happens? Level of neutral buoyancy. And you see this is often referred to as an anvil shape. You can see the flat anvil shape here. And these high clouds that are formed as a result of that, and these can then be carried away into and form cirrus clouds. These have a very strong long wave effect, but a very small short wave effect. So these high clouds are warming, and the low clouds are cooling. And these are these high cirrus clouds that are these wispy clouds whose altitude is more than 4 kilometers typically, and have a very strong greenhouse warming effect. Okay, guess I want to cover one last thing, and that is clouds and climate uncertainty. We talked a lot about how complicated this is, but we want to look at we want to try and quantify, even in a simple approach, how clouds can affect the warming that we predict. So for that, we'll go back to this energy balance model. But even before that, so think about it. In a warmer climate, you might have either more or less low clouds. So if I have less low clouds, would that lead to warming or cooling?
Cooling.
So less low clouds.
Warming.
Why warming?
Because low clouds. Cool.
Low clouds cool. They reflect sunlight. There's less of them. That's a warming effect. Great. Excellent. If I have more high clouds, what effect would that have?
Warm.
More high clouds have a greenhouse effect. More greenhouse effect means warming. And the numbers are such that if the distribution of high clouds or low clouds changes only by 10%, it's equivalent to a CO2 doubling easily. Okay, so these are small changes can make a big difference. So now the claim here is that we generally estimate that in a warmer climate, low clouds and high clouds will change such that they will add to the warming. So if clouds don't change at all, the expected warming for doubling of CO2 is basically 2 degrees. Okay, doubling of CO2, 2 degrees, if clouds don't change. If clouds do change, whether high clouds or low clouds, this could increase the warming. And so when you hear someone saying that the expected warming is, say, 3 to 4 degrees, we know that without changes to the clouds, the warming is only 2 degrees. So that additional degree from 2 to 3 is due to the effects of clouds per doubling of CO2. And that effect of cloud is very uncertain, hence the big uncertainty range that you always see. This is a demonstration of how uncertain this is. These are different contributions to the energy balance in 12 different models. GCM is a global climate model. So you can see that the part in the energy balance that's very different from model to model is the brown part, and the brown part is clouds. So the other parts in the energy balance are more similar, but as you get to the clouds, there's a huge difference between the different models because each model represents these complex processes in a different way, hence a different prediction and hence a different projection of the global mean surface temperature. Okay, I want to show you one last thing because you'll need it in the Jupyter notebook for the homework. So how do we quantify this effect on of the clouds on climate uncertainty? So we go back to that energy balance model that we had before. So you remember 2 layers, a surface layer and an atmospheric layer. Let's go one by one here. Ignore the left-hand side for a second. What does this term refer to?
Shortwave radiation that reaches the Earth.
Right. Alpha is the albedo of the atmosphere. So some of the arriving radiation is reflected, so S times 1 minus the reflection is the net shortwave radiation, sunlight, that reaches the surface. That must be balanced, so that's the input. I see that we have another input here. What's this input reflecting? What does this represent in the energy balance of the surface?
Is it like how much long wave radiation is radiated down?
Exactly. This is the atmospheric temperature, sigma T to the 4th times the emissivity. This represents how much long wave radiation arrives to the surface from the atmosphere. This is the natural greenhouse effect. Now, you can see that it's written here as a function of the CO2 and the atmospheric temperature. We'll get to that in a second. And then finally, what does this represent? So this is the temperature of the surface, comes with a minus sign. So what does it represent?
Surface radiation.
Yeah, this is the long wave radiation from the surface upward. So we have a source due to shortwave, another source due to the long wave radiation from the atmosphere, and a sink due to the radiation by the surface upward. Is that okay? Great. And this is the energy balance of the atmosphere. So now we have This is how much energy is arriving long wave from the surface, T, and then how much radiation is lost by the atmosphere. Remember the factor 2, because the energy is lost both up and down by the atmospheric layer. Okay, as opposed to last time, we now include dt dt. So before we just assumed that these are all in balance, but in general, if they're not in balance, this would either increase the surface temperature or decrease it. So we need to solve these equations and find the steady state. And the way to do this is the rate of change of the temperature depends on whether the source is larger or the sink is larger. That would determine whether the temperature is increasing or decreasing. And this is the heat capacity of, say, the upper ocean and the atmosphere. And similarly for the atmosphere, if the source is larger than the sink, the temperature in the atmosphere would rise, and it will rise until they would balance each other and reach a new equilibrium. So this is exactly what we did before, except I've added this time rate of change here on the left. Any question about this? Right, we plotted this. We plotted this in the following way in the past. We had incoming radiation from the sun minus some reflection, and then we have long wave radiation from the atmosphere and long wave radiation from the surface. This is up. The temperature here was TA, and temperature here was the surface temperature here, and the sun is here. Rings a bell? So these are the equations that describes this system, okay? Nice. Okay, now come the clouds. So looking at the albedo, for example, we now understand that the albedo is due to these low clouds. The low clouds, we can assume, in a very simple framework, depend on the surface temperature because they're close to the surface. So we're assuming that depend on the surface. There is this proportionality constant that tells us to what degree is the albedo of the clouds changing with the surface temperature. This coefficient could be positive or negative. So let me ask you a similar question to before. If delta SW, delta shortwave, is positive, would you say that low clouds are a warming effect or a cooling effect in a global warming scenario? Okay, it's a complicated question. Let me try again, okay? This is the reflectivity. It appears here. If this thing is positive, what does it say about the albedo changing as the temperature warms? Does it mean that the albedo, that the reflectivity of the clouds would increase or decrease with temperature? Increase, right? If this is positive, then as the temperature of the surface increases, this entire albedo will increase. Is that so now? So this means that if delta SW is positive, the albedo of the low clouds increases with temperature. Is that a positive effect of warming or a negative effect of warming? Negative feedback on warming. Negative, brilliant. Because as the temperature increases, the albedo increases. That reflects more sunlight and cools back the Earth to what it was before to some degree. So it acts to cancel some of the effects of CO2. Okay? Make sense? Okay. Here's another, and of course, if it's negative, the opposite happens. So if the clouds respond by becoming less reflective with increased warming, it means that the low clouds would add to the warming. Similar with the long wave. So we can assume that the emissivity of the clouds, this is the emissivity that appears here, atmospheric emissivity. So the atmospheric emissivity, of course, it's a function of CO2, as we know, but it's also a function of the clouds, and this is how we represent the effect of clouds. So if delta long wave is positive, it means that the emissivity grows with the atmospheric temperature. So higher atmospheric temperature would mean higher emissivity of the atmosphere. Would that add to the warming due to CO2 or reduce the warming due to CO2? So again, if delta LW is positive, the emissivity grows with temperature. The emissivity of the atmosphere grows with temperature. Is that a warming feedback or a cooling feedback?
Warming.
It's a warming feedback. So you can tell that the sign of delta LW and delta SW decide whether the clouds are positive or negative. And now if we choose their values and we solve these equations, here's what we are getting. So first of all, suppose these deltas are just 0. This is the no feedback situation. We start with some temperature, we increase the CO2, and we reach some equilibrium, new equilibrium, because the CO2 stopped increasing after 100 years. Is this figure clear? So again, the CO2 is increasing for 100 years, then it stops increasing. As a result of that, the dashed line, the temperature with no feedbacks, increases and then saturate. This is the new temperature. And the increase in temperature here seems to be about 3 degrees. Now we're adding the cloud effects that we just described. It turns out that the temperature for the deltas we chose increases now, instead of by 3 degrees, by 5 degrees, roughly. So this is a case where clouds have a positive feedback on the warming. Of course, you could change these deltas and have a negative feedback. And this is what happens in this case. The emissivity goes up and the albedo goes down. You'll do all of that yourself in the workshop, but I'm hoping this gives you an idea of what this is all about. Yes?
So the impact on the long wave radiation like outweighs the impact on the short wave radiation.
Well, it depends. Let's see. You see, what happens here is that the long wave emissivity is decreasing, so that is a cooling effect, right? No, sorry, this is the albedo. So the albedo is decreasing, that is a warming effect. And the emissivity is increasing, that is a positive effect again. It looks like in this scenario, both the short wave and the long wave, so both the low clouds and the high clouds, add to the warming. You could come up with a different scenario in which they oppose one another. The changes to the low clouds and high clouds oppose one another, maybe even completely cancel. Here it happens to be a case where both add to one another and to the warming due to CO2. Let's just jump to the conclusions. So we saw that clouds have a huge effect on the radiation in the atmosphere, both on long wave radiation, the heat escaping from the Earth, and on the short wave arriving from the sun. And these two effects can even cancel each other in the present day climate. So the high clouds warm and the low clouds cool, and the net effect, as we discussed, is cooling. And we saw that clouds have a huge part in the uncertainty in future climate projections that we make, and we talked about why. We generally believe the cloud feedbacks to lead to enhancement of the warming by CO2. But based on everything we learned today, you understand that that belief is problematic. I think it's robust, but quantitatively, it's a very hard quantity to determine with no large errors. Now, people suggested various negative feedbacks by which clouds would eliminate global warming due to CO2. So far, no one was able to come up with such an idea that would say, look, clouds would actually completely eliminate the effects of rising CO2. There are many climate skeptics who believe that, but no clear scientific evidence so far exists that cloud can eliminate the effect of CO2. On the contrary, right now, the consensus seems to be that clouds would actually amplify the effects of CO2 a bit. So clouds have been and continue to be the most important and poorly understood aspect of climate response to CO2. All right. See you next time.